Hello, my name is Kwon. In this video, I'm going to talk about approximate decoding for network-coded interdependent data, which is published in Signal Processing. For this paper, I have worked with Professor Hyunggon Park, Professor Nikolaos Thomos, and Professor Pascal Frossard. I will start this presentation with introduction and move to consider the system setup. After that, I will explain the proposed solution and show experiment result in sensor network scenario. Finally, I will finish this presentation with conclusion. In recent years, Internet of Things is growing rapidly. This rapid growth is causing data explosion in networks, especially filled with sensor data. As the characteristic of an IoT network, the sensor data can be highly correlated and mostly loss tolerant. And the IoT network builds multiple unicast flows because it has huge number of monitoring devices. In order to handle a large amount of data, the network should have a high bandwidth efficiency. Moreover, since IoT devices are mostly wireless, stable network condition is not guaranteed, so system needs to be robust against data loss. In order to overcome such challenges, we propose to deploy network coding. The network coding is a relaying architecture that combines incoming packets and forwards the combined packets. The well-known advantages of network coding are throughput improvement, reduction of delay and power consumption. Because we are considering multiple unicast flows, we can take advantages of throughput improvement by deploying network coding. However, alternating problem becomes the main challenge to deploy network coding. Since network coding combines multiple packets, the decoder can start reconstruction only if it receives at least the same number of packets as the original messages. If the decoder cannot receive sufficient number of coded packets due to the packet loss or bandwidth variation, the decoder cannot reconstruct the original message at all. In order to overcome this problem, approximate decoding is proposed. Approximate decoding allows immediate reconstruction even though the decoder doesn't have a sufficient number of coded packets. However, approximate decoding relies on a strong assumption of a source model. Source data are assumed to have a high similarity. For example, in adjacent video frames, the pixels at the same location can be very similar, so approximate decoding uses additional equations derived from the source model. Source data are identical. However, such identical source model becomes a strict constraint, and if the original sources are not identical, the performance of approximate decoding is significantly degraded. Therefore, in this paper, we aim to improve performance of approximate decoding by considering generalized source model. As a generalized source model, in this paper, we consider interdependent source data. Recall that IoT data has high correlation between neighbored data sets. For example, brightness changes in consecutive images, temperature, humidity, pressure variations over time, and seismic signals at adjacent sensor locations. In these examples, the difference between values in source vectors can be characterized by a unimodal distribution, and this is called interdependent source data. So, n plus 1's source vector becomes n's source vector plus delta n. Here, delta n follows a unimodal distribution. Next, we consider network coding deployed network. In a multi-hop network, network coding has three processes: encoding, re-encoding, and decoding. After data are collected at source nodes, the encoding process combines multiple packets into a single packet. In this combining process, source data are multiplied by coding coefficients. In this paper, we use random linear network coding so that these coding coefficients are randomly determined at each node. In network coding, the operations are performed in Galois field. If Galois field is not used, because the re-encoding operation has addition and multiplication, the required bit for a single value might be increasing over hops. However, by using Galois field operation, the required bit for a single data can be remain constant. After encoding process, network coded packets include coding coefficients as a header and the encoded data as a payload. When the packets are delivered in multi-hop, re-encoding is required and coding coefficient metrics are correspondingly updated. At the destination node, the decoder waits until it receives the same number of packets as the source package, and the reconstruction can be done by the inverse of coding coefficient matrix. However, if the decoder receives only Kn coded packets when T packets are combined, the coding process becomes underdetermined problem. So we have all or nothing problem here. In this case, approximate decoding can give a solution by adding extra equation based on identical source model. In this equation, for finding x, coding coefficient matrix C and D should be full rank, so we can have inverse matrix. The approximate decoding proposed to design D as matrix filled with zeros except two elements of a value 1 for each row, and vector nu as zero matrix. Again, this design is based on identical source model. So, our next problem is how to design vector nu for interdependent source model. Technically speaking, the new problem is find the vector nu that minimizes decoding error of approximate decoding. Our problem can be written as find the argument nu that minimizes expected cost, which models the decoding error of approximate decoding. Before I explain cost function, I would like to talk about this figure. This is a simulation result of a decoding error in approximate decoding when nu(n) is used in the system if the true value is nu(n star. The decoding error is measured by Peg-mean square error (PMSE). So PMSE means higher PMSE means lower decoding performance. In this figure, the error is minimized only when nu(n) is exactly same as true value nu(n star. This is very interesting result since usually as the system parameter becomes closer to the true value, the decoding error gradually decreases. However, in this figure, the decoding error of approximate decoding are approximately the same, except the case where nu(n) is exactly same as true value nu(n star. This can be well captured by Cauchy-Dirac delta function, so we designed the cost function using Cauchy-Dirac delta function. Here, C nu(n star means that the amount of decoding error when nu(n) is used for approximate decoding if the true value is nu(n star. Let's look at the second part of the expected cost, which is the probability of occurrence. Since we consider interdependent source model, the true value nu n follows psi delta, which is a unimodal distribution with mod delta. By solving this optimization problem, we find that the mode of interdependent source distribution, delta, minimizes expected cost of approximate decoding. Based on this finding, we propose to use delta for vector nu. For this solution, the decoder only needs to know a single value delta instead of a full distribution, and this is proposed as mode-based approximate decoding. We compare the proposed solution with other strategies. In strategy 2, with full knowledge of distribution psi delta, we randomly sample a value from the distribution. In strategy 3, without knowledge of distribution psi delta, we randomly sample a value from uniform distribution. So the distribution results are presented in the figures on the right side, which shows the PMSE for different standard deviation. In these simulations, for unimodal distribution psi delta, we use Gaussian distribution and Laplacian distribution. In both cases, we confirm that the proposed solution with the blue curves shows the lowest decoding error. So far, we find the vector nu in approximate decoding for interdependent source model, and we conclude that by using the model of unimodal distribution, the expected cost can be minimized. However, we can still improve the performance of approximate decoding. Let's check again the performance characteristic of approximate decoding. In this figure, as we already discussed, if the system parameter nu n and the true parameter nu n star is not the same, the performance is significantly degraded, and the closeness of nu n to nu n star does not affect performance. This means that the performance depends only on the number of nu n that is exactly the same as nu n star. So, our next goal becomes how to minimize the number of zeros in the difference between nu n and nu n star. But in here, there is a new challenge. Because source model is defined in real field, but network coding is performed in Galois field. Even if the xn plus 1 minus xn is delta in real field, the equivalent Galois field operation may result in not only delta, but also other outcomes. This means even though the delta is enough information in real field, it can't be sufficient in Galois field. Let's look at a toy example. Here, the difference between these two source vectors is always 16. However, the Galois field operation results are not always 16, and it sometimes becomes 48 and sometimes 112. So, in order to solve this problem, we propose to provide additional information called PSI. In this example, since 16 has a Galois field candidate 48 and 112, we save the position index of each candidate. So for example, the position index for 48 is 5 and 8, so we provide the position index 5 and 8, and for 112, the position index is 3, so we provide this 3 to the decoder as well as delta. Then here we have a new question. What will be Galois field candidate of delta? If we can know the candidate from delta, we don't need to send the information to the decoder. And next, By using additional information, how much performance can be improved? So we can control the amount of information for our target performance. The answer for the question are shown in property 3 and 4. We show that if delta is in form of 2 to the k and Galois field size is 2 to the m as used in network coding, there are at least n-k candidates for delta, and the nth candidate delta n is expressed as follows. And we further show that if the nth candidate delta n is additionally used for approximate decoding, the performance can be improved by a factor of 1 over 2 to the n minus 1. So, in this figure, we can confirm that as the number of information provided in decoding increases, the decoding error decreases by half of a previous result. If delta is not in form of 2 to k, we can use algorithm 1 to find the candidate. The key idea in this algorithm is to express delta as sum of 2 to pj and use of a candidate for each 2 to pj to find the candidate of delta. So, in summary, we propose position similarity matrix PSI for approximate decoding that include delta by default and position indices of candidates. The number of candidates n should be determined to meet target performance that can be calculated based on property 4 and network bandwidth to support the size of a PSI based on property 3. By considering the trade-offs, n should be properly determined. In order to confirm the performance of the proposed approximate decoding with PSI, let's look at the PMSE for Pascal rate. The left figure is when delta is 8, and right figure is when delta is 10. In these figures, PSI 0 means it includes only delta, and PSI n means it includes PSI 0 as well as position index of n additional candidates. In both figures, we confirm that as increasing n, PMSE decreases, which means lower decoding error. In this simulation, we observe PMSE over overhead size for 3 solutions. The first one is Park 2003, which is the original approximate decoding, and second one is mode-based approximate decoding, which includes only delta, and the third one is PSI. Since the original approximate decoding and mode-based approximate decoding requires less amount of information compared to the proposed PSI, for fair comparison, we allow retransmission in order to make the same overhead size. Here, the overhead is defined as the amount of additional information over the amount of original information. So, for example, 25% overhead with retransmission can be achieved by retransmitting 1 additional package per every 4 packets. So in this figure, red curve denotes original approximate decoding, and blue curve denotes mode-based approximate decoding, and gray curves are PSI for different Pascal rates. From these results, we confirm that PSI has the lowest PMSE compared to the other 2 strategies, and the performance of PSI can be controlled by overhead size. Now, we use the proposed solution in a real sensor network scenario. For this experiment, we use actual seismic signal as source data. The seismic signals are captured from 30 sensors placed at a distance of 100 meters by each other. As the distance to seismic center from each sensor increases, The signals are mostly time-shifted and energy-scaled signals of other sensors. Energy difference between signals are captured by the Gaussian distribution with mean 8 and standard deviation 0.2. In this experiment, each sensor makes measurements and forwards data to its neighbored encoding sensors. The encoding sensor performs a random linear network coding in Gaussian field 2 to k and forwards the combined packet to the receiver. Then, the receiver collects packets and performs decoding process. Here is decoded signal by proposed solution. The first signal is original seismic signal, and the second one is decoded signal based on mode-based approximate decoding, and last two signals are with PSI with different amount of information. We can easily observe that the decoding performance improves as more information is used. Such information improvement also can be confirmed by PMSE and PSNR values. In conclusion, we build a robust and efficient data delivery system by using network coding and approximate decoding. We improve the performance of the original approximate decoding by generalizing source model for interdependent sources. We firstly propose mode-based approximate decoding and enhance its performance with PSI. We also theoretically analyze how much the performance can be improved by increasing PSI size. We finally show the experiment result with actual seismic data and confirm that the proposed system works well in a real-world scenario. Thank you for your attention.